pleasure to introduce Aaron, who will be speaking on geometric Satake.
All right. So geometric Satake is a categorification of classical Satake, which very briefly is an isomorphism of the spherical Hecke algebra with the representation grain of Langlands Dual Group. I won't write this on the board, so if you're familiar with classical Satake, you'll see how each step sort of is getting geometrized in the process. Yes, so the critical ingredient here that everything sort of lives in, the world in which we will operate, is the Affine Gassmannian. So we'll start with the geometry of the Affine Gassmannian. Okay, so Grassmannian has two N's and two S's. Most important spelling check. All right, so let G be a reductive group. Let's assume it's over C. And let O be the ring of power series, one variable. K, the fractions of the ring of power series, aka the Laurent series. The Affine Gassmannian is a geometric structure, it's a variety. I'm going to put that in quotation marks, it's technically in the scheme. We'll eventually discuss what functor this is more specifically, but not yet. Whose C points are the quotient of the O points of G, the K points of G, mod the O points of G. So for us, that will be sufficient, and I will be able to discern enough geometry from this. And we are going to call this piece PR sub G. All right. The first example is, of course, whenever we're dealing with reductive groups, the most basic case is a torus. And in this case, GR sub T is TK over TO. And there was a canonical bijection of this with the co-character lattice of T, which is the collection of homomorphisms from the multiplicative group to T. And it goes like this. You actually sort of, it's a bit tricky to write it down. If you write it down for semantics, it's very simple, but if you write it down in terms of pairing with co-characters. So if chi, so this is we say z lambda is the point corresponding to the unique disconnected connected component of this corresponding to lambda for lambda in the co-character lattice, and we define as follows. It's the unique point in GRT such that the order with respect to z of chi of z lambda. So there's going to be some point on the torus. So and chi is going to be an arbitrary character. It's equal to a lambda for all chi in the character lattice. So obviously you can take a chi, you can apply it to an element of a torus in TK. This will give you a particular element of K. You can ask what the order of Z is, and the point is that gives you an integer. So that needs to agree with the pairing with chi. So that's the technical sort of description of it for a torus. So it's a very simple discrete structure for a torus. So now back to general G. So note that GK, so this is as a group, this is a group whose C points are the K points of G, acts on the Affine Gassmannian on the left. Right? All right, now we're going to pick T. Oh, maybe I should. No, I T and G of axial torus. There's a natural map from GRT, GRG. And we will let L lambda, this is the notation in Merkovich-Belonen, be the image of the point Z lambda in GRG. All right. So notice so we can consider TC, right, as a subset of TK, which is inserted a subset of GK under this identification. And again, we have this action on the left, like this. These L chi, observe that these L chi are precisely, these L lambda rather, are precisely the TC fixed points. I'm just going to write, when I write the C points, I'm just going to write the usual letters. So from now on, that will just be T. G will mean C points of G, fixed points of fixed points in geometry. All right, now we're going to come to the basic thing, which is consider GO living in GK, and we consider the right action restricted, the left action rather restricted to GO on the affine correspondence. So we're going to consider the GO orbits in the affine Grassmannian. These are parameterized by double cosets, O mod GK, O. So if you're familiar with the Hecke algebra, you'll be recognizing this double quotient space. And they are actually uniquely parameterized by the co-character lattice T modulo the action of the Weil group, which we can associate canonically with just a set of dominant co-characters on T. And the association is a point L chi is in the same orbit. Is in the point L chi, and you have to consider its GO orbit for all chi, for all lambda in co-character lattice. So for two lambda that were the same W orbit, these give the same left GO orbit. And we're going to define for G lambda to simply be GO L lambda. Okay. This of course goes for all lambda, but particularly those dominant ones.
I think you want co-characters here, right? Not characters.
Characters? Did I just verbally say? Yeah, these are all co-characters. Oh, no, I see what you're saying. I put the wrong side there. No, that is correct. Sorry. Yes, these are all co-characters. Right. Oh my god. That would cause geometric Satake to go completely the wrong way around. This is correct now, and this is correct. Okay. So at some point, I'll make sure that my written notes have it correct. I'm supposed to be careful on the board. Okay. Yes, everything is parameterized by co-characters, and for each W orbit in the co-character space, there's unique corresponding left GO orbit. Thanks, Justin. Thank you so much. Very important detail there. Okay, so all right, so choose a Borel. This gives us a system of positive groups. Let n equal to the radical of B. For dominant, so now we have a notion of dominant. Now this gives us a preferred choice of dominant groups now, associated with RP. And so we have for dominant lambda and mu, we have the following property geometric or topologically within the Grassmannian. So we have the following basic property, which is the mu orbit is contained in the closure of the lambda orbit, precisely when lambda minus mu is a sum of positive cohomology. This is standard. Now, so I'm just going to briefly describe a touch more of geometry, which is yes, so consider the orbit G, and again that means BC points, so G is L lambda. This is isomorphic to the flag manifold G mod T lambda, where T lambda is a stabilizer of L lambda in G. It is a parabolic group whose Levi factor has Levi factor associated to the set of simple roots killed by lambda. Now, right, we're going to introduce a character that is not, strictly speaking, in the character lattice of the torus at all. It's something you would introduce as a kind of affine root if you're doing this really properly, but we'd Merkovich below it if you want to see how they do this correctly, but I'm just going to introduce in an ad hoc manner. We're going to introduce a character called delta check, which is a map from GM to the automorphisms of our field A, which is S maps to the map that sends Z, our sort of parameter, our uniformizer, to SZ. All X and Z. Observe that GR lambda, the lambda orbit of our Affine Gassmannian, is precisely the set in our Affine Gassmannian whose attractor radius under the action of delta check S on X is in G L check. So as a consequence of this, you can see that these orbits, these GR lambdas, which are these basic building blocks of the Affine Gassmannian. Oh, I should mention these are all finite dimensional bona fide varieties, which is, and they sort of live as in a enclosed nested filtration, giving us the whole Affine Gassmannian. So when you're setting up the in-scheme structure on the Affine Gassmannian properly, you always want to reduce to sort of these GR lambdas, and then you consider sort of nested contains closed embeddings. So these are all bona fide finite dimensional varieties, and I'm about to give you a description of them. GR lambda is a G equivariant vector bundle over G mod E lambda, thought of as this orbit G times so this looks like G at lambda, so it's this G times at lambda, C points of G acting on the point at lambda. All right. All right, now we're going to introduce the ubiquitous rho, which is the half sum of the positive roots. Associated to B. These are Borel. And we have the dimension of this is precisely two rho, which is a character applied to our lambda, assuming that we've chosen this to be dominant. I'm going to skip that. This may be perilous. There are these notion of negative infinite orbits that we're going to be that we're talking about, but I don't think any. I think they ought to show up in a proof, which I'm going to have to skip the lack of time. So I could say this at my own peril and have to be enforced later. So this may be the point which I discover myself later in the talk, but for the sake of time, I'm going to immediately now introduce the critical extra ingredient in the Affine Gassmannian that was due to Mirovic and Beilinson. So we're now going to introduce the semi-infinite orbits. So for each new in our cocharacter lattice, consider the variety. Consider the orbit, let's say. I'm not going to call it variety just yet. Now, these are the k points of n, our unipotent radical, acting on the left on LB. These are what we're going to call semi-infinite, the semi-infinite orbits. They have neither finite dimension nor finite codimension, which is why they're somewhat strange. And intrinsically, they are actually indices. But the intersection of any of these with one of our spherical orbits is a bona fide variety in every case. So here are the basic properties of the semi-infinite orbits geometrically. So
Sorry, nu is a co-weight again, right?
My God, I don't know why I have this. Thank you so much, Justin. Yes. Every time.
And it's the orbit. It's the orbit of is that supposed to, does that say n of k?
Yes, and these are the k points of n. Yeah.
Got it. Okay.
Yeah. Apologies there. And even again, I even wrote it down. I don't know if the camera can see it, see that I got it right, but I censored it. But no, I'm getting it wrong again. So no matter how many times I do this, I'm going to get the wrong number of odd, which is exactly what you don't want if you have a duality situation. You have to get everything parity matching. So here are the properties. But yes, thank you so much. Do not hesitate to call me out if you see an error like that on the board. Okay. So here are the basic properties. I will not prove these properties. This is proposition 8.1 in Mirovic-Beilinson. So A, the risky closure of one of these semi-infinite orbits is equal to the union over all co-characters less than or equal to nu. Next step. Again, under our standard ordering, where we assume that less than means that the difference between the two is a subpositive roots. And B is a sort of a technical point, which I won't dwell upon too much. It's that within each X's closure, the boundary, I suppose you might be assuming complex topology to make this meaningful, but at the moment let's just assume complex topology because it's simpler, of S nu is a hyperplane. He does actually use this in arguments, hyperplane section under a projective embedding of the whole Affine Gassmannian. Now we're going to introduce sort of the opposite orbits of these. Now, there are various kinds of opposites that you have here. Ones where you deal with Z inverse as opposed to Z, and ones where you deal with B off as opposed to B. That's we're going to be dealing with a B off B sort of opposite here. So we're going to introduce the opposite orbits. EU. For new, I'm gonna get, don't you worry, Justin, I'm gonna put this in the right place. There we go. For new again, a co-character of T. And this is simply going to be let B be the opposite for L. and minus the opposite unipotent radical. And these are simply going to be defined as T means n k points minus, this is an int. Anytime you're dealing with k points, things you have an int structure. If you were dealing with O points, it tends to be a variety, but just infinite dimensional, not a finite type. But if you have k points, you do need to have an int structure. Times L. All right, so now we have the sort of basic geometric component that goes into the ingredients of this of the geometric Satake proof. So again, the way I've structured this, I'm not mentioning any sheaves on the Affine Gassmannian until I've got to make sure I do before the break until 30 minutes. So we're close. So we're going to at 4:30 we're going to introduce the sheaves on the Affine Gassmannian. At the moment, everything will just refer to the structure, the geometric structure of the Affine Gassmannian itself. I don't know if that's actually the right way to do this pedagogically, but it's a natural fit. So okay, so we have now, yeah, okay. I think this deserves its own board, so I'm going to go back over to my. So this is a theorem. I do have a proof in my notes, but I'm not going to have time to go through it. That would take us into a break probably. Not that it's particularly hard. It's just you have to use that hyperplane fact many times. So you have the intersection of the spherical orbits. If and only if L nu is in BR and bar. This case, the intersection with the closure is pure of dimension rho nu plus lambda. But we're using lambda be dominant. And then sort of, I'd say dually, but I'm not sure if this is exactly the right way to use that term. I'd say oppositely. T nu intersection GR lambda is not empty if and only if L nu is in GR lambda bar, in which case T nu intersection GR lambda bar is pure of dimension minus rho nu plus lambda, where lambda is chosen anti-dominant. I thought you might be able to write this more elegantly so that you never have to choose a representative that's not dominant, but it actually makes it more complicated to put the minus sign on the inside, so don't even try. I'm just following Berkovich loading here is the best way to do this. And I'm going to make one observation, which would have been impossible had Justin not pointed out that I wanted my star in the upper point of X here. I wanted these to be co-characters as opposed to characters. This point, this toric attractor locus, this fixed point of T, is in the closure of lambda spherical orbit, if and only if nu is a weight of the irreducible representation of the Langlands Dual Group over C. Well, I mean, Langlands Dual Group is always over C, so I probably put that there, of highest weight. All right. So, any questions? I think we're at the 4:30 mark, so it's time to wield out our perverse sheaves now. So far nothing has said the S word. Now it's time for us to change that. So, word of warning, there are very different conventions, I think, between L-adic sheaves and D modules. I've been bifurcating between two different sources. Ryan Reich's notes from the 2019 H3 seminar, which is D modules, and very much below it, which is sort of classical intersection cohomology / ecological cohomology, so L-adic stuff. And so it's possible that I may mess up functors, so hopefully Justin will be able to catch it. Or anyone in the audience can catch it if I use the wrong formalism or mix formalisms. But okay. So okay, I'm slightly lying. There's one little corollary here. That's a great sort of importance here. So because of this description, we can actually describe, we can have a very efficient bound on dimensions, which will be of use to us. So a corollary of this is for any dominant lambda in R cohomology lattice, and any T invariant subset in the closure of our circle orbit, we have that the dimension of X is less than or equal to the max over all the individual points L nu in our toric fixed locus of that should be a pretty good. All right, so now we're going to introduce the category spherical. Cohomology, not fair. Cohomology. There's so many O's in that word. I suppose everyone who's given a talk that involves the word written out actually doesn't notice that. All right, so so what are we going to be considering? We are going to be considering the category of GO equivariant. So under the left action wheel, of course, perverse sheaves on BunG, which for sort of formal reasons should be the same as the perverse sheaves on the quotient. Of course, there's a subtlety on the double quotient, that is the itself quotient. There's a slight subtlety, which is that, of course, this is in the object. So you're simply going to define it as limit as you take GO equivariant perverse sheaves on GER. I forgot my case well. So this is defined to be this, and this of course is not yet quite meaningful, and this is going to be by definition limit as lambda limit or limit the direct limit of our GO equivariant perverse sheaves on their lambda are under the standard order here. So each individual perverse sheaf will be scored on some finite Schrodinger on some scheme. you then can ask, well, hold on, why is GO, like, does GO equivariance not make this sort of unwieldy because GO is sort of not an infinite type? The answer is no, because we'll always filter through a sort of finite algebraic group, and the thing they're pushing out by is going to be is not going to contribute anything that would make this sort of no longer work. I sort of like in some cases. I'm not, it's not quite, it's not quite fair to say this is pro-unipotent, it's GO, right? Well, okay, I'm not sure.
Sorry, what's
My comment is the reason that this works, this GO equivariance condition isn't so unwieldy is sort of for technical reasons that I'm slightly shifting under the rug, but it filters through a sort of an actual sort of an actual algebraic variety of finite type reaction on these varieties, so that you can take this limit without any problem. But there is this detail about things being pro-unipotent, right? That allows you to then say that the cohomology change, or is that not needed?
exactly like G of O has this first congruent subgroup that's pro-unipotent.
Okay. Yeah.
And the point is like equivariant sheaves for something unipotent or more generally pro-unipotent embed fully faithfully into the category of sheaves, so it sort of doesn't cause any problems.
Yeah, that's the technical. Those are the technical words which I didn't want to, which I was going to garble. So that's said correctly. Brilliant. So
one question actually: are you putting a finiteness condition on your D modules?
Ooh. I don't believe so, but I should I be? Do you think it'll run me into trouble if I don't?
So you can write this formula and it's correct with no finiteness conditions as long as the colimit is taken in the category of co-complete DG categories. So like in particular, in that context, it's not true that any D module is supported on some Gur lambda bar. Rather, it's like any compact object is supported on some Gur lambda bar, and in general, something is a filtered colimit of such things.
That makes sense. Okay, so yeah, this was probably if we're using the problem, then so interpret with the grain of salt. Most of the computations here will be formal statistical not matter too much, but it is worth thinking, and it's kind of an interesting subtle point that I ought to spend a bit more time preparing and thinking about. So okay, so now we have now I can state the theorem that we are going to prove. So goal. Here I probably do mean the finite spherical category. So SPA is a symmetric monoidal category where it makes a symmetric monoidal structure. And moreover is isomorphic to rep G-checks. Okay, where G-check will like rep, look out there, Langlands Dual, which is a complex.
Sorry, so your D is perverse sheaves. It's not. It's like the abelian category of D modules.
Yes, I think I do want perverse sheaves in this case, from the order that I've done here. Okay, well that meant I think yeah. Okay, so, yeah, perfect. Okay. Yeah, I think that's probably going to save me issues because there was a point where I started using more Mirokovich-Volonin than Reich's notes. So yes, okay. So the point is that this category has an actual product structure on it, which we're going to discuss, and there's a function from it to rep GL, and the product structural convolution product will map to tensor product of representations, and this will actually be an equivalence of Beilinson categories. So that is the big theorem that we're going to try to prove. It can be upgraded and modified in various ways too. But the way we're going to prove this is actually kind of interesting. It was pointed out by Mirokovich-Volonin in their paper that in some sense, what we're going to do is we're going to actually just have an abstract. We're going to show that this is an abelian category with the correct kind of properties. And the product we're going to show admits a commutativity constraint. And we're going to actually establish a fiber functor, which sort of by the magic of the Tannakian formulas automatically implies that it's equivalent to some category of representations of some group. And so once you've done that work, all you need to do is identify the group in question. So it's a question of checking the combinatorics. So what we're really going to be doing here is we're going to be, I don't think we'll have time to go into checking all the combinatorics here, but we're going to be simply analyzing the sort of fiber functor of the spherical Hecke category here. And in doing so, we'll automatically actually give a very natural definition for the Langlands group. The dual group. Now, of course, Langlands Dual Group is always defined as the group whose group data is dual to the original group, but so there's something to check if you want to show that it's actually GL, but you can just define GL to check to be precisely the group that the Tannakian formalism says exists, and whose category of representations it's precisely spoke. So, all right, so basically, here's the program of attack. I need to produce a fiber functor from this to that. And it's going to be called the global cohomology functor. We have our sort of diagram that we've seen analogs of many times. So we have third B, third G, third T. Oh, it's B use T. What we're going to do is we're going to consider more or less this. This is not quite, this needs to be modified a bit. We're going to pull back along this tab and push forward along this tab. And because this is completely discrete, one can see that we'll put them over this. There's going to be a weighted vector space weighted by the co-characters of T. And so this sort of begins to look like the kind of thing we want. Also, if you're familiar with the classical Satake picture, it is precisely pushing it onto a function of the torus that you have to establish that the Satake transform is. So this is going to be our sort of trick. Of course, we have to be precise. So we're going to have to go get ourselves down to the geometry here. So, all right, so we have the following theorem. And in this geometry, we will use all of these semi-infinite orbits that we've discussed so far. So this is Beilinson-Drinfeld theorem 3.5. All right, let's A, the element of our spherical Hecke category. We have canonical isomorphism. Practically supported with cohomology. SD with coefficients A to the case restricted cohomology. Moreover, that's a sub T. So this is on the opposite with one. This is K. Compactly supported. Oh, okay. Sorry, sub C. Yes. So this is the canonical isomorphism. And moreover, this vanishes. Both sides vanish. If K does not equal to rho U, and this immediately implies that the functor F mu from our spherical category again, I'm making some field of coefficients, but I'm sigma K given by one point where it's non-zero. this be on this side of this. That's needed constants within different exactness properties in two different equivalent cohomologies. So I think I have this next. So I now yeah, so I'm actually going to prove this. It's a magnificent proof, and it involves something that we have discussed before in the seminar. So that A, an element of our spherical Hecke category, eta be an element of our play characters, dominant. Then lies what's sheaves. So when you restrict it to this stratum, the perversity applies as a complex of sheaves in degrees less than or equal to in for eta, which as we want to see is -2 rho. I.e. A restricted to or eta is an element of D less than or equal to O eta. All right, so actually this is not using the full weight of perversity here. This is standard animal complex. Perversity plus the fact that the compactly supported cohomology of this intersection is 0 if A is greater than the dim dash. A is greater than the dimension of our intersection. Which is equal to 0 mu plus eta. Imply that H is supported. Is equal to 0 if A is greater than 2 rho. All right. So we're just doing some classics, looking at the cutoff points of these complexes and where they start to vanish. Okay. We may filter the Affine Gassmannian by these those. I think they're also called Schubert cells. These things, I call them spherical orbits by these closures, these spherical orbits. So that HC can be written in terms of S nu GR nu. So by a sort of spectral sequence argument, then on and that should be a secret packet. Spectral sequence argument then gives us that HC S nu alpha is to 0 if K is bigger than nu. And a very similar analogous argument on the T's as opposed to the S's shows us that zero if K is less than T. Okay, so together that implies that all we need to do is show that these are isomorphic and we have no vanishing condition, because the one will give us the one and the other one will give us the other. So now comes the sort of critical moment in the proof. Okay, so we're going to find an action of GM on our Grassmannian. So prove iso suffices. So we're going to find an action of GM on our affine Grassmannian by the co-character 2 times the sum of the positive code, 2 times the sum of the 1/2 the sum of the positive co-roots, which is the same thing as the sum of the positive co-roots. And the fixed points here are L nu and all right. We're to write this out since we're about to be ready for a break. Over here. Once more, we're going to use this sort of toric geometry implicit in the affine Grassmannian to great effect. S nu is going to be the set of points in the affine Grassmannian such that the limit is x greater than 0 of 2 rho s x becomes L nu, and T nu is going to be the points in the affine Grassmannian such that the limit as s approaches infinity, the repeller locus of x is L nu. And now this isomorphism is on the nose consequence of Beilinson, which we discussed last quarter. So you have an attractor locus and a repeller locus, and that allows you to sort of swap the shrieks and the stars, which in this case is the difference between the two different kinds of cohomology, which are practically supported in the scanning cohomology restricted. So bring and this. So, all right. I'm just going to write a theorem, and then we'll go to break. So, we have a natural equivalence of functors immediately because of this. We apply the global cohomology. That. Which is sum over co-roots HC 2 rho B not B nu. This can be right, that is E Lanlgands V from spherical event. This is a sort of consequence of the above. You probably can see why. It's because the two different the two different isomorphisms split the sequence. So you split this cohomology. And so I won't write out in full because it'll take about half a page. It's very obviously going to follow from this. But yes, the two different isomorphisms split this, and so you get a direct sum decomposition like this. In fact, it's also independent of the choice of T and B. That's a nice geometric argument, but I won't go into that. You can see it in the work below. So I think that this is an okay point for us to take a break, with the caveat that we may have to leave a tiny bit over out the second half. What do you think, Justin? Do you think I should? Do you think we're set up to be able to do the convolution and its commutativity constraint?
Yeah, seems fine.
Okay, so let's go for a break for 10 minutes. This is the problem, you only know at the end whether you screwed up. So all right, so the last little thing I'll say before we get on to the convolution product is that as immediate corollary to all the above, write it explicitly, corollary to all of the above, we have the global cohomology functor. H star. Also called F, from sp vect is faithful and exact. Exactness follows from the above. We have not checked faithful, but it's a one-line argument to check that it's you don't kill it on zero. You don't kill it on zero thing. Fine. A non-zero element of stuff. So now, convolution.
Sorry, what was the faithfulness?
The global cohomology functor from Satake is faithful and exact. Can you read that? Is it clear from?
Oh no, I'm just wondering, was there an argument for faithfulness, or?
No. I said there is one. It's in Lanlgands. We haven't covered it yet, and I was not gonna. I mean, it's like it is one argument. At this point, I could have done it. It's one line. But okay, I'm trying to cut to the like, trying to cut extra weight from the talk so that we get to the commutativity constraint without everyone having fallen asleep by then. So okay, so the convolution product is the next thing we're going to have to do. So we're going to draw out our diagram. This is the, as I say, the analog of tensor product, and or at least it goes over to tensor product on the rep side. So R GK times GO R GR. Okay, so we have this chain of maps, and the maps go like this. This projection, in the obvious sense, projection the projectional factors. This map Q is the obvious projection modeling out by the GO action. So GO acts on this by a sort of right. So GO inverse ancient. Oh, that's the action there. And multiplication is you simply multiply the two. Of course, it's independent of this inner modeling out by the GO action. So the three maps are given in this way. So P and Q is its standard projection and its multiplication. Okay, so we're going to define for A1 and A2 in SPA. We're going to define A1 involved, A2 via Rn lower star A, A twiddle, where A twiddle is the pullback. I'm going to apply this to the zero perverse cohomology of the external deriving product. Okay, so what happens here? We have an A1 and A2 living over our affine Grassmannian. We pull them back, we take the zeroth perverse cohomology. Now, the point is that a pullback of an equivariant sheet here will be equivariant with respect, will be an equivariant sheet with respect to the right geo action here. So Q is actually going to be an equivalence. So you can actually think of this as sort of a Q pullback inverse applied to that. So what we're saying is there exists a unique A twiddle. Let me get this precisely right here. Yes, so yes, sorry, this is where. Yeah. So there exists a twiddle living on this associated bundle on this product quotient, which is defined by being the unique. Its pullback, and this is a pullback is equivalence because it's an equivalence of right geo-equivariant categories here and which is acting freely on GK. So it's the equivalence of so the sheaves here are equivalent to right geo-equivariant sheaves here. And again, that's because geo acts freely on GK. I'm trying not to have to write down too much on the board here. I hope I'm not making it too confusing. So therefore, there exists, if you have a sheet here, there exists a unique sheet that gets pulled back to it here. And so this defines sort of one wrong direction now. And then you push it forward along the multiplication. So you tensor, you sort of move equivalently to here, and then you the convolution you push forward multiplication. Again, at the level of functions, this corresponds exactly as you would expect to literally what we would call convolution of two functions, from an integral of f times g. And yes. Now,
sorry, what's the purpose of taking perverse H0 here? It's not necessary, right?
No, it's definitely not. That's about to be my next comment. That
okay, sorry.
The reason that Merkovich-Belonen do so is because they're working with arbitrary rings. They then have to prove something. But it is not needed in this case. So what they say is, there's a proposition to sort of make this really clear, which is maybe it's not even a proposition. It's a proposition for Merkovich-Belonen, but it's note A1 box A2 is automatically perverse. At least when your coefficients are yields. All right. Now, so that this extra thing is not necessarily just this extra perverse H0 is. Now, the one thing that is not obvious, it's a beautiful thing. I think it's called Raphulus by Beilinson-Drinfeld. Paper, a big book. If A1 and A2 are the geo-equivariant perverse sheaves and Grassmannian, then so is all right. So let me even outline this. I give the full print in my notes, but I didn't have time to look here. So there is a notion of a semi-small stratified map. And a small stratified map. And I'm going to actually give definitions. Okay, so semi-small. So, yeah, so let's make this correct. So we have a map from x to y, from it's y to x, f, and we have a stratification of t on y and s on x. Stratification. And F is going to be simply locally trivial with respect to the stratification. And we'll assume the strata are connected. Locally trivial. And then F itself is stratified. All these sort of technical things are going to have to write down, but that just means that F of T is a union strata for T and T is a union of strata S and stratification. And also, if I take a strata and look at its preimage, so F inverse S happening to S, I consider this sort of F, just seeing that component is locally trivial in stratified sense. Now we can define the two notions. I think I'm going to try to do them in parallel, in tandem here. So, all right. F is stratified semi-small. If A for all T map F restricted to T is closure is proper. All T, and this is a really critical constraint. Any S in S such that S lies in the image, so 4. And the S and S lying in the image of F. We have mention F inverse X section T bar is less than or equal to half function of F of T bar minus index. Any this little triviality therefore all. Non-fancy, yes. So what this is doing is it's really sort of describing a growth rate on the dimensions of the fibers. As the codimension below gets smaller, you're allowed the fibers to grow above if you restrict yourself to smaller dimensions of the space. So roughly half the rate which you're carving out the codimension. And this is a non-strict inequality, and basically a small one strict with they add a couple more constraints, they add a couple more desiderata. So, but map F is small if there exists a non-empty dense W contained in Y, dense stratifying W in Y, such that A for all of T and T, the map added for straight to T prime is problem. B map F restricted to W, mapping W to its image is finite. And W is a prefactor of its image. And then C is the equivalent constraint on dimensions, but with strict in it. It's a slight technicality, which doesn't matter, just to say the same thing over which you need to interact with this dense stratified subset W. But yes, dim and line is less than strict 1/2 T minus dim S. So I wanted to write those down because those are actually very important. What do these actually give you? They give you preservation of sort of perversity under push forward. This is the sort of slogan here. So I think push this one out. So I wanted to write them down. I didn't write them down before. They may be sort of common knowledge, but insofar as this is a learning seminar, we might as well have the definition written down here. All right, so there's always this lemma. If F is stratified semi-small, then R F streak A is not for the streak, this is a star, R F star A is an element of the perverse complex associated with the S stratification. A in if F is small, then for any such W, as the definition, and A W, okay. We have we first take the intermediate extension of A, and then you could push it forward, and this will really push forward and then the intermediate extension of define J and J have exactly second. Or J that's W to X, J middle maps F and W W to Y, and this one maps W to X. Okay. So sort of commutation of push forward and intermediate extension functor. Okay, so as you can, so basically when you have a semi-small map, perversity behaves very, very well. And so what do Markovich and Loden show? They show using precisely the dimension estimates that I described with an outline above, using sort of T invariants. They show that M is stratified semi-small with respect to the geo stratification. So I won't go through that. It is dimension counting argument, and it's precisely the kinds of things that it's always been set up, so we always do it as an exercise. But yes, so now we can go on to the final. point, and maybe the most important point of our meeting this week, which is the commutativity constraint. So a priori, it is not at all obvious that this convolution product is symmetric in the two inputs. I mean, it clearly isn't in the definition. And this is about as obvious as saying at the level of the spherical Hecke algebras that convolution is commutative there. Again, convolution of a non-commutative group, you would not expect it to be commutative, but sort of miraculously it is commutative. And so we're now going to describe the commutativity constraint. And the fusion product. So this is the point at which maybe the sort of, you actually do use a very new sort of geometric idea. I've tried to sort of compare it to the classical story, and it wasn't actually clear that the classical story you sort of have to be ordered, you have to consider you have to sort of break up the sum into smaller components and realize all the counts are the same. Sort of commutativity of Hecke actions. But in this case, there's a very beautiful geometric argument that basically reinterprets the convolution product as the same as the fusion product, which is on the nose symmetric. And the idea of this was Beilinson-Drinfeld, at least in concept. So to do this, we're going to have to interface with a sort of global version of the Affine Gassmannian. So this now we're going to have some. Now we're going to talk about the Beilinson-Drinfeld Affine Gassmannian. Oh, right. Okay, so X, a smooth algebraic curve. Notice that everything we're doing has been entirely local. So we're open Laurent series and form power series. Now we're going to introduce global curve. If X is X, if X is an X, we're going to call OX the completed local link. And KX will be defined to be the punctured formal disk with a fraction field of OX. Yeah. For all C algebras R, going to that XR equals X times spec R, product over spec C. And we're going to define XR star to be X minus X. So Beilinson, which we discussed in Tom's talk 2 quarters ago. Will show us that the local version and the global version are related, in fact, the same. So Beilinson implies that GRX, which is the Affine Gassmannian, which is sorry, GKX mod GOX, can be interpreted, and this is for any X, as the in scheme. And again, the in scheme is defined as a functor. So you take your C algebra R, and it will spit out F, a G forcer on XR, nu the map from G times XR F restricted XR punctured trivialization. On XR. Okay, so you can glue at the formal disk at one point. Choice of trivialization of the formal disk is all the different ways you can get a global G forcer here, and that's what we lost. Now the idea of the Beilinson-Drinfeld Affine Gassmannian is to allow this point X to move, so that you consider something sort of fibered over X. I mean, naturally speaking, this seems to involve choice of point, and we'll like to express that. So in fact, we can do even more than that. We can trivialize with multiple different points at once, and so we're going to actually perform this sort of over an arbitrary number of points, considering in each case the totality of points over X. So let Xn be our product, not symmetric product. There's going to be an Sn action of X with itself, and consider the functor R maps to the interval of points R points on X. F a G forcer on XR. Nu sub 1 x1 through xn. This is actually quite a lot to write down. And for that, I feel Justin's pain, but last week I trivialization of F on XR minus the graph dx. Okay. Where xi are the collection maps here instead are. So, okay, so consider x times argument. This is the graph of these maps xi. We're going to remove them, they're closed subspecies. We're going to trivialize x away from the we're going to trivialize x away from the union of these things. Okay, so this we're going to call GR sub XTN. I remember that from last week too. I managed to avoid it so far. I mean, rather kept it in my throwing of the board, but yeah, this is great. There must be some sort of magnet up there. So observe that the affine Grassmannian global n-fold affine Grassmannian is a fibration over xn with the fiber given by a product of affine Grassmannians. Okay, where is the set x1 to xn, but yi's are the same. So kind of an amazing thing happens here, which is that when points collide, the fiber will actually shrink. which is the opposite of what you would expect in normal algebraic geometry, where it's upper semi-continuous, and therefore the fiber should get bigger. But this is because this is a quintessentially infinite dimensional thing. If you look at it on individual spherical orbits, it all becomes the same again. That's discussed beautifully in BunG's article. All right, so now we upgrade our convolution product. I'll write gr sub x for gr sub x to the 1, right? You only really need 1 and 2 in this case. So everything here lives over x squared. And I've got to define all the terms in this sort of math for you. So this is the point where the writing starts to get, we'll see how much of this Hagoromo chalk that was full at the beginning makes. But everything here is actually fairly straightforward. You just got to keep your wits about. All right, GR. So this I define as the product of two affine cross. Okay. So what is GR x times GR with the sort of wiggly hat on it? This is a functor that for a given C algebra R will map us to x1 comma x2 squared R. And then it will give us two torsors, F1 and F2. And it will give us two maps VI, trivialization of each Fi on XR minus the graph of Xi, for I is 1 and 2. And it's also going to give us a map U1, which is a trivialization of F1, or first, only our first G-torsor, on the punctured disk, on formal neighborhood of X. Okay. So yes, so what do we have? We have our two G-torsors. We're trivializing them away. We're trivializing each G-torsor away from its corresponding point. So then this is trivialized away from X1, this is trivialized away from X2. And for F1, we are going to actually give a specific choice of sort of trivialization on the sort of family of formal disks on X2. Okay. And I now owe you an explanation of what PR with the smaller twiddle times PRX is. I'm not sure how to read these things loud anymore, to be honest. It's really gets paragraph clear. These things are to be seen, not spoken. Okay. This is again two little points, R points of X. F1 and F2 are G-torsors. On XR. U1 is a trivialization of F1 on XR minus X1. minus gamma minus the graph of x1. We have an extra data of eta. Okay, I should probably write this down here. Which isomorphism of F1 restricted to XR minus gamma X2 with I see. I should just have F1 and this my second one should have no space. We're gonna have two G courses, one of which we'll call F1, one of which we'll call F. To make it clear that there's a sort of asymmetry here. And then we're going to trivialize this F1 away from the graph of X1, and then we're going to have an isomorphism of F1 with F on the complement of X2. Okay. Okay, so what is our map P? Is simply to forget B1. Oh, by the way, note that every single one of these maps, every single one of these not maps, every single one of these spaces is fibered over X2. So we're just going to forget the X2 data because of the isomorphism central itself in both cases. So P is to forget A1. Okay.
But the spaces also literally equal to spaces to the before.
Literally equal to the.
Like, they look like they're the same. You have this. I mean, instead of the long twiddle, you can write or
So that was GK times GO, wasn't it? In the previous one.
Yeah.
Times
curve.
GK times curve, right? And then this was GK times over. Oh, yeah, no, these are very analogous. But well, but these are all fibered over X2, right? So I mean, these are all much bigger. These are all like allowing you to vary the point. This is doing that. These are familializing the maps that you described. This would be the analog of the convolution Grassmannian, but in families and yeah. So there's no natural map from the previous thing to G to X2, right? Whereas this one really does. X same on the diagram. Yes, no, these will turn out to be the same on the diagram. Yes, very much so. That's going to be that's the punchline. That's why the fusion project will restrict point lies to the thing. So on the diagram, yes, that's what you're sort of tacitly thinking. I apologize. This is a bit tricky to sort of, fit one's head around. I had to spend a bit of time thinking about it. And if I don't use my notes, I'll get it wrong. So okay, so that Q. This astounding array of data, and this will map to.
Oh, so it's first of X, like the X is this is the BG one, not the.
Yes.
It's not a little X.
So this is big. This is big X, big capital X. So so just a word of my own terrible handwriting. My X's letter little are always backwards C forward C, and my big X's are always cross.
X, and I thought they're all.
Oh no! Oh my God, no! Oh no! This is big. These are all fibered over X squared. Yeah, it's a little tricky to make these things work. Both handwriting wise, yeah, my little X's are like curly. Okay, so Q is going to be defined by map. Okay, so it's not really a moment. It's just saying that's the same kind of data that you see in Q. Go. Okay, where F is the deforcer obtained by gluing F1 on XR minus gamma X2 and F2 on the cylindrical neighborhood, formal cylindrical neighborhood, R family of X2 disks using ISO U2 composed mean 1 inverse, which will have F1 on intersection of XR minus gamma X2 with XR X2. So on the sort of punctured cylinder. Right? And now lastly, I've got to tell you what M is. So it takes in the data of F1, nu one, F, and eta, and I've got to spit out an F and a nu. And nu here is going to equal, simply it's got to be it's multiplication, so it's going to be, it's obviously going to be 1 XR. These are defined in a common domain, along that, I suppose. Okay, and now my last barrage of symbols, and I promise we will then be off the races. My last barrage of symbols for you is what the meaning of the global analog of GO is, and how it acts on everything. So let's, yeah, so finally, global analog of GO. I'm going to call this GX. GX. And this is going to be given by a functor, a K algebra, it will spit out, a C algebra rather, it will spit out XM, and XNR. F is the trivial. Sorry. On XR. Mu X1 with XN, a trivialization of F on so here we're trivializing on each disk. Trivializing on each disk, we have a trivial bundle, but then we're sort of giving a potentially incompatible trivialization on each disk. So now I'm not gonna write this down because it'll get very, very good. These act on these by sort of whenever you have an isomorphism, you can imagine how it will sort of act on the gluing data or act on the trivialization. So that's how we're going to, that's how this thing will act on the various, on the two spaces in question. And so again, what we have here is we have a notion of a convolution product. And so
also blow trivialization of F, or which take it such a direction.
I mean, it's yeah. So you can take this to be g times x, and you're just replacing that.
More than okay.
Yeah. So I mean, you could pick a specific one. In this case, it wouldn't make any difference. You know, there's no. It's still. These are all set value functors. So there's not. This is not going to be automorphisms. It's not stacks. Yeah. Okay. So yeah. So. Yes, so I think probably since we have 10 minutes left, defining all the actions. Actually, 10 minutes left. Maybe I should democratize this and hold up to a vote, but I think actually we probably can. It probably would be. Oh, okay, so okay, so yeah. So we're going to define the convolution product. So B1 and B2 are equivariant x. And we're going to define it by v1 times v1 convolution v2, and we'll put it, making sure that's done globally with x. Is going to be the push for multiplication map of the twiddle, where again we're going to be testing using some kind of isomorphism of Q. Q pullback of the twiddle is the pullback. I'm again going to include this here, but we're going to quickly see that there's no problem. Box. Okay, so we're going to define the convolution part this way. Of course, I tacitly need to explain to you how my GXO acts on these spaces. Okay, so we'll do that, and then I think that will be the last horrifying bit of sort of nightmare for the speaker to have to write down. I think the audience is probably good to see it all, but it's really very nasty to write this all down. Your hand gets hurt, your algorithmic shock is dies down to not something. So okay. Yes, if you're taking notes really furiously. If you're just watching, fantastic. This must be, a joy watching a speaker be this pedantic. But I feel it would be sort of a little dishonest to it's a shame we couldn't get them all in one board. We'll get all of them different things. So yeah, if this was one height, this would not be a problem. So GRXO acts as GRX by altering okay, so first thing, Logan Oslo implies that GRX is equivalent to R F G torsor on X R X completed and new X a trivialization of F on X. That's equivalent to GR1, GRX1, equivalent to Affine Gassmannian. And this is that first one. Right, so then GRXO acts on this. But also new one.
Sorry, is it supposed to be GXO? I forget your notation.
Ah, yes. Oh, thank you. Thank you. This is a group. This is GXO. Wow. I hope I made that mistake elsewhere, but well caught. Wow. Shows people are really paying attention, so I can't afford to just go on autopilot here.
Also,
yes.
I'm going to be annoying and point out that the formal completion minus the graph is empty.
Oh dear. Yeah, so I guess I probably want to say KX somewhere in there, don't I?
Yeah. Anyway, just worth mentioning. It's like you have to do something.
Okay. Touche is my response there. Yes, you don't want this to be an empty set. That would be a very boring functor. Well, GXO will still act on it. Maybe no, okay. Okay, so yeah, Drinfeld did some amazing empty set logic the other day, and so I can't write with that.
Sorry, what is G?
GXO is this group here, global analog of GO. So again, this is a kind of group scheme over X to the N, right? You have these torsors on X on XR, and you have these trivializations on each formal neighborhood on each formal disk. So that's the analog of GO, globally speaking. So GXO acts on this by altering U1, whatever this new means, because you need to remove this sort of, central line from this. You will need to be a little bit careful about it. But yes, okay, so yes, okay, and okay, and now we have it acts in two ways. One, we view GXO as a group scheme over X squared by pulling it back along the second equation. Then GXO acts on GRX times GRX. Bit long twiddle by altering U1. Yeah, the wire here, but we'll, I think, be able to finish with something coherence. Okay, and two. All right, last one. Last of these cubic brackets that we have. Two, right. As is to R for I equals 1 Fi G torser on XR I again the non-empty set version of whatever this means. U1 privatization of F1 on XR. Okay. So we're going to view GR as a group scheme where X squared pulling back along the second projection. GXO that acts by modifying both U1 and U2.
Give a description of the GXO orbits in the BD Grassmannian using like the dominant co-character. Is there an analogous?
I need to think about it. I'm sure there is probably so like point by point, but you have to live over each point individually. So I need to think about that a bit more because of course, what is the BD Grassmannian? It's kind of looking as this family of affine Grassmannians over the curve. So you'd be taking sort of family of Schubert cells, fiber thing, that probably degenerate at the diagonal, but they would degenerate the correct way. They degenerate upper semi-continuously. So yes, I think Zhu discusses how to think about this geometrically in that way. It's a little tricky, but okay. So anyway, this gives us all the correct actions now for completeness' sake. I've actually said something meaningful. And okay, so the last few comments I'll make here about how this all goes through. Okay, there's one more diagram, and then we're off the races. So no more horrible definitions. So this defines everything. We have the following theorem: M is actually stratified small Not just semi-small, it's actually stratified small. And that's basically because over the diagonal, it's stratified, it's semi-small, and over U, which is x squared minus the diagonal, it's just an isomorphism. So over U, and it's an isomorphism. So it bumps everything up a dimension so that the inequality becomes strict, and then it's we have this dense locus, which is the U, so it actually is stratified small. And okay, and the last thing we'll do, and then you're all free to go, is the commutativity constraint, which is the very last thing that we have here. So if you'll bear with me, I know we're hitting the time, so this was meant to be done 5 minutes ago, but unfortunately, all these things. All these statements, weighty statements about what trivialized what and what was mapping to what, dominated the last 15 minutes. At least they're on the board, and so modulo any typos I make, they're understandable. All right. Okay, so for simplicity, the commutativity constraint. And I'm going to say the commutativity constraint is not actually the commutativity constraint. We need to modify this, unfortunately, but we won't have time to go into detail about that. But this shows you commutativity. So let x equal a1 for simplicity. And this is the point where we're going to actually alter things, slightly warp things, that we're picking a favorite coordinate, and this will make it no longer the commutativity constraint that you actually want in general. You have to modify it by a sign convention to get everything to go through. So this is where we cheat. Justin explained to me beautifully how you can get rid of this by just doing it canonically from the beginning, but that wasn't written up in Murkish Bellonian, so I was confident in my ability to reproduce it faithfully. So okay, so this gives a global coordinate, and this in fact trivializes per x over x. Okay. We're gonna borrow this, which is the one. This is the one that we're going to borrow this because we're running out of battery too in all senses here. Everything's collapsing. Okay, so
That's the
really idea. Okay, I may have to do just that. But yes, I was not expecting, the link to actually literally run out of battery. So we're going to restrict your x squared to diagonal. And let's see if I can describe this. So there are two functors that he so yeah, so we have x squared. This is diagonal third x. This maps to third x squared. X or x times per x. Okay, so I think we have J for the open, I for the closed. And
I don't think you want fiber product over X, right? It's just straight up product.
No, I certainly do not. You're right. I put too many X's there. Yes, just straight up product. It's 2 copies of the Affine Gassmannian. Yes, I should have. Okay. If I had a high enough IQ to be able to remember this and be confident in this. This is the diagram we want. And okay, we're at 7%. This should be enough for it. Will die a hero's death. So we're gonna be down to the line. So okay, we now define I naught equal I upper star -1. This is all just to sort of make everything work when you have the extra dimension of the curve. And this is a map from curve from curve dxo. X A to curve GO. Remember, we have this global coordinate now, so everything is written as a product. Okay. Right? So this is how we plug everything into here. And we're going to take so now for A. For GO of our affine Grassmannian. We have define also one more functor. Functor. Okay. So you have A. Isomorphic ray star of perverse H0 of TO A1. You B 1 2 1. A follows from smallness of M, and B follows just from definitions. And now comes the payoff. Fusion our convolution product this way. Same thing as right? But this is manifestly symmetric in the two arguments. So now you can swap these freely, and you get finally is isomorphic too. So restricting to any point on the diagonal, we see that A1 involved A2 is isomorphic to A2 involved A1. It's a beautiful kind of argument where you use this sort of technique of fusion that on the diagonal. On the diagonal, the points collide, so you get a copy of the affine Grassmannian. So, but away from the diagonal, it looks exactly like a product, and so you can use the fact that you can extend from the off diagonal locus onto the diagonal locus using this Schroeder-Schrieb functor, and because there it's just a symmetric tensor product, it's just an external tensor product, it's obviously symmetric. So my last little words, and I'll just say this word is not writing on the board. That is the commutativity constraint. That's the hardest part of the argument. And there's this beautiful sort of geometric way using this global Affine Gassmannian Beilinson-Drinfeld to see this. I don't think this is directly analogous to the technique used in the classical Satake transform. The last thing is, of course, unfortunately, this isn't quite this gives you isomorphism, but this is not the isomorphism you actually want. You have a sign convention, which is due to the fact that we pick this coordinate. Once you get that right, of course, you also need to convince yourself that the Lanlgands Dual Group is the reductive group whose representation category is the fiber functor in question. That's a combinatorial argument. But this shows you that that SPA has all the relevant properties and of sort of being a abelian commutative, abelian tensor category with a sort of commutativity constraint on the tensor product. There's a symmetric monoidal in particular, and it gives you the functor to next that will give you the fiber functor that's relevant. So everything here allows you to find the dual group. So I think that sort of concludes the main steps in the proof of geometric Satake, and thus my talk. Thanks so much.
Given that we have like geometric way to make everything, that means we can upgrade everything with like homotopy coherence and another structure on like the derived category.
So the answer, I think, is yes. Justin is on exponents, right? So Justin, this is the question about whether we could upgrade everything to the homotopy coherent derived category, right?
So the convolution product is defined at the level of TG categories. The fact that it's symmetric on the abelian category is kind of a little bit misleading. Like the convolution product is definitely not symmetric on the level of DG categories. It just so happens that it's more like at the level of derived categories, it's more like E3. So it's like not fully commutative, but then on the abelian category, an E3 monoidal structure is actually symmetric. So somehow it's like the factorization structure, this fusion product is contributing E2 and the convolution is contributing E1, and so you total up to E3, and then if you're working with at the level of one categories, like that actually forces you to be commutative on the nose.
Thank you.
Maybe I can make one comment because I have to jump off, but
so sorry,
yeah, if you look at Ryan Reich's notes, he does a slightly different approach to this that I think is interesting. So you can prove that the convolution and fusion products coincide in a slightly different way by using nearby cycles. You do some kind of local acyclicity argument, right, to show that the this kind of outer convolution and that convolution and fusion agree. And so in particular, you can avoid using smallness. And in fact, you can avoid it completely. So we used it earlier to prove that the convolution product was exact. But if you prove that the convolution and fusion products agree without using smallness, then it follows that the convolution product is exact because this fusion product is sort of manifestly is perverse, right?
I see. Yeah. That's actually an interesting one. I hadn't understood how Wright had managed to avoid smallness, but that is the moment he does it.
That's the reason, because again,
that was why I felt I understood this proof better. So maybe I used a slightly outmoded technique here. It's interesting. Okay.
Well, it's just it's a different argument, but again, like you can express this intermediate extension in terms of as a nearby cycles functor, and then it's sort of exact, by construction. So if you show it coincides with the convolution, then you get exactness automatically. So you have to make some kind of it's just different. You make some local acyclicity argument instead of a smallness argument.
Yeah, fantastic. Yeah. So yes, okay. I can just mention aloud to everyone that the three references are, if you want, basic Affine Gassmannian, Jim and Zhu's article, which was discussed 2 quarters ago. Ryan Reich has these two papers from notes from Gatesbury's 2009 seminar, the first talks of the later quarter in that seminar, and then this is just Mirkovich Beilinson. And another reference which I found helpful, if you want this sort of relationship between this and convolution theory and the classical, is Pramod Achar's book, Perverse Sheaves, Representation Theories. It's a big fat encyclopedia, as a whole chapter. It's very well written, very clear. But Thank you so much, Justin. I know you have to go. Thanks so much. I'm sorry for keeping you over time here. Apologize to your daughter on my behalf.
You just
Signed
signed off and said thanks, sir.
Yeah, exactly. That's good. I feel really bad. But thank you all for staying, and that was nice to meet you.